Okay, I'm not going to bother with an introduction because this is just a continuation of where we left off with gradient descent part 1. If you recall, we discussed how the algorithm worked. We were confining ourselves to a one variable equation here, this parabola. We talked a bit about how the algorithm works, how you pick an estimation of where you think the minimum is, and this rule for updating that is what we talked about here. So basically, the gradient or the derivative in this one-dimensional case tells you which direction the function is increasing or decreasing. So we're going to step in some direction which decreases the function. So that's the negative of this gradient, and there's the proportionality constant gamma, which we'll talk about in a bit, and we just do this iteratively. So the next step, you'd again evaluate the derivative, figure out which way to move, take your step, and so on until you reach some desired tolerance. And this was the implementation thereof. There is no actual cutoff criteria. It just runs through all the iterations in max iter variable. At some point, we'll probably put in some sort of cutoff criteria, but for now, we'll just loop through all these iterations. The only change I made to this function from the last video is to add this debug statement in here, which is set to false. And when it's set equal to true, it prints out the guess of each of the roots. So if you recall, we ran this function. The minimum of this parabola up here we got was basically minus 1.25, which is the actual value. So that was cool. But before moving on to the multivariable part, I want to talk about a couple of things. First is the effect of this parameter proportionality constant gamma in this equation up here. The second one is local versus global minima. This algorithm basically just finds the local minimum, so that's potentially an issue. And also, I just want to make a note of the fact you can use some sort of estimate, numerical estimate of the derivative or gradient if for some reason you can't, excuse me, if for some reason you can't actually calculate it analytically. So let's start off here quickly, and I'm going to insert a cell here, and I'm going to copy, I'm going to copy this, paste it in here, run it. Okay. You know, now that I think about it, I want to change the way this debug code works. So I'm going to shut off the recording and make some alterations here. Okay, so what I did here, and this is kind of sloppy, is I added the ability to pass in the objective function. The function will be called f in here. And I changed the debug thing to return the value of the objective function that we're actually trying to minimize at each iteration point, as well as each guess of the root. And then depending on, and this is what I think is really kind of sloppy, depending on if debug is on or not, it'll return either all four of these values, or just the root, not the root, the minimum and the count. But yeah, a bit sloppy, but I'll fix it later. So let's go on and just play around and see what happens when we change this gamma value. So a couple things control the size of the step here. Obviously, as the derivative gets smaller and smaller, your step size automatically will become smaller and smaller, but you can scale that by this gamma parameter. So generally, you want it to be a relatively small number, but not so small that you just drag things on forever, or you get stuck and never reach your goal. So let us, for example, come in here and set that gamma. Where do I want to do it here? Let's go here and say gamma is equal to 10 to the minus 9. Kind of be a little bit ridiculous. Let's run this. And you see we really never get anywhere. We get a so-called minimum of roughly 4, which is where we started our function to begin with. And the reason for that is gamma, the derivative is whatever it is, I forget, we calculated it up here somewhere, 21. So we're multiplying it by 10 to the minus 9, so our step size is too small, and we're only doing like 100,000 iterations, so we never go anywhere. The reason I wanted to return, this is the place where, yeah. The reason I wanted to return the value of the function we're trying to minimize, and I called it j here, is that we could see what's going on by just plotting that. plt.plot j. So you see we never plateau. So if we go back up here and make this 10 to the minus 3, which I think it is by default, run the code, you see we collapse down and then we basically have reached some sort of, the algorithm has converged. So that's what happens if it's too small. Potentially if it's too big, for the time being, I'm going to comment that out. And I'm going to change gamma to be, let's just make it 1.5. It fails and we get a not a number. And what's going on here is our step size is way too big. And if we look at this plot, what's happening is it's jumping. Let me change the limits on here and make this, that's the y limits. Let's just make this minus 10 here. And then get rid of this x limit. So what's happening is we're starting at 4 and then we're just taking a big jump that actually puts us higher on the negative side. So the slope is bigger, so the step size gets bigger, and we would jump to the higher point here, and then it just keeps blowing up to infinity, and then eventually we get something like infinity minus infinity, and that's where that not a number is coming from. And we can probably visualize that with the plot. Oops, come on. You see it just blows up. And it does so after only like 200 something iterations. Let us scale down this y value to, I don't know, let's do plt.y lim, I don't know, let's go minus 2 to 100. $1,000. And let's make these dots. So this obviously is increasing very, very fast. I didn't think it would increase quite this fast. Let's go. Damn, this thing just blows up instantly. So I was kind of hoping to get a better visualization, but you can tell from this what's going on. So this gamma is a factor that you're going to have to tweak yourself. So let's just put this back to something sensible, like 10 to the minus 3. Okay, let's go on to local minima. So, okay, let's consider this equation here. It's a quartic equation, and I've entered the code in down here to plot it out. So if we look at this, this has multiple minima. So you have this valley here, which kind of sits at a higher elevation than this. This is the global minimum of the function, but gradient descent finds only local minima. So depending on where we put our starting guess, we could get either this point or this point here. So let's actually, I'm going to code up this function here and pass it into our gradient descent, and we'll just pick some different initial values for the guess of our minimum, and we'll see what happens. Okay, so I've coded up the function itself and its derivative here, and now we're just ready to go. So we're going to do an x0 and a count is equal to gradient descent. Quartic derivative is the name of the function, quartic derivative. And we're going to start at a point, I don't know, let's start at minus 2. Let's print out x0 and see what happens. Minus 0.1, that looks about right. Let's actually just plot it out. So let's go plt.plot x0 quartic at x0, and we'll make it a circle. So there we are. That looks good. Let's copy this code and try a different value for our initial guess. So we're going to copy it. We're going to paste it. And instead of minus 2, let's go here. Let's go, I don't know, how about 6? I was not expecting that. It came back to this minimum. Oh, I put minus 6. Well, that'll do it. Where's my plot? So you see here when we put a value of positive 6, we get this minimum here, this local minimum, rather than the one which we would prefer to get, which would be the global minimum. And that's an issue you're going to have with gradient descent, especially if the number of variables, in your equation, like this is a one-dimensional equation or two-dimensional or three-dimensional. If that number is small, the number of dimensions, you can get this quite readily. It doesn't tend to be as big of an issue for huge systems where you have like these neural networks with hundreds of thousands and millions of adjustable parameters because, well, it might be clearer when we move on to multidimensional systems, but basically the derivative in every single direction has to simultaneously be 0 to be a minimum, and that just doesn't tend to happen very much. But okay, let us go on, and the last thing, I don't know why this is like that. The last thing will be just a numerical estimation of the derivative or the gradient. Now you notice in all the examples we've done so far, where's my function here? We wrote a function that actually calculates the derivative, and so the reason I chose polynomial functions is just because it's very easy to calculate this by hand, but many times you may not be able to. So let me, I'm going to go back to this quadratic equation here. And I'm going to pretend I can't calculate out the derivative, and I'm just going to find a way to numerically approximate it and then use that numerical approximation in our gradient descent algorithm, and let's just see what happens. So down here, I'm going to write a function called derivative approx, and it's going to take an argument f, which is going to be our function that we need to differentiate, the point we want to differentiate, and I'm just going to put in an args variable just in case we end up needing it. So what I'm going to do here is return, I cannot type, return f at x0. Actually, I'm going to put also in a delta or epsilon value here. I'm going to call it delta. And that's just going to be equal to some small number. And I'm just going to do, I don't know, 1e minus 7. We can adjust that as needed. So it's going to be f at, or x0, or f at x plus delta. And we're going to subtract f at x minus delta. And we're going to divide all of this by 2 times delta. So it's basically a central difference approximation for the derivative. So let's run that. Does that run? Cool. It does. I've been actually writing out whole functions, but you can use lambdas for this. So let us actually write the derivative of our quadratic equation here and say, what do I want to call it? Let's just be original and call it my deriv, and that's going to be equal to lambda x args. Let's call this derivative approx. We're going to pass in our quadratic equation, so quadratic is here. I don't know, let's just pass in none for an argument. Does this actually work? Let's actually run this with a number. Let's see. The derivative at 4 was 21, so let's just try. My deriv at 4. Do I need to pass in the args? Yeah, I do. That should be an x. Well, that's not right. Let's just see here. Am I missing a parenthesis around here? Close here. Why is this double wrapped? I probably just misplaced the parentheses. Run. 21, was that our number up here? Where is it? 21. Good. So we can now use this expression here, our my derivative function in our gradient descent. So let's just plug this in and make sure it actually works here. So I'm going to get rid of this, and I'm going to say x0 comma count is equal to gradient. The function in this case is going to be my derivative, and we're going to start at 4, and then we're going to print out x0. Awesome, minus 1.25. So that's an option if you cannot analytically calculate the derivative. It's just a quick and easy way to do it. It's not the most efficient thing computationally, but sometimes you got to do what you got to do. And kind of just as a reminder, this is more for pedagogical purposes, this code. If I would actually write this, I wouldn't actually probably, if I had to write it, I probably wouldn't do it in Python. It would be in C. And Python, SciPy in particular, already has a bunch of optimization functions built into it. So the minimize function, I can type in our quadratic minus 4, and it'll do basically the same thing for us. So here's our minimum. So this is, again, is more for educational purposes, but yeah, it's a good idea to know how these work. And sometimes you do have to code up your own routine because there are issues with the canned routines that come built into the system. Okay, I can see we're up to already 17 minutes, and I wanted to keep this short, under 10. So I'm going to do it in 3 parts. The next part will be the multidimensional case. I'd like to do like a logistic regression, a linear regression, and a logistic regression. So hopefully I don't have to split those and do a part 4, but we'll see what happens. So yeah, until next time, I will see you.